Student Professor Dr. Dolphy Gilpin here, and we're continuing with plutonium. We're continuing with plutonium, and with special honor to and commendation to our professor at City College, Professor Morrow. I don't know of his status at this time or his existence, but from that time he adopted me during a live telephone communication, and I'm here saying that that professor must have had a great vision. So I've given him honor at this time as we go through some chemistry. And because of the course Chemistry 103, I have separated the element 103 just for say, which is lawrencium. We're going to focus on lawrencium. He taught Chemistry 103, so I said element 103, lawrencium. Also element 108, representing Chem 108, and also there's a bit of a Chemistry 234, which was organic chemistry. I'll probably have to use their atomic weight of a 234, which would be in the region of plutonium and uranium here, and radon isotopes that have atomic weight of 234. Yeah. So those would have been the courses taken at City College in chemistry. So here we have continued with plutonium, and so we have polonium-210 is more radioactive than plutonium, and burning plutonium with thorium is an alternate way of plutonium, which is usually combined with uranium to form MOX fuel. So to get this MOX fuel, we burning plutonium with thorium. This is an alternate way of the plutonium, which is usually combined with the uranium to form MOX fuel. Now, if plutonium-239 absorb a neutron, we're going into some nuclear reaction here, its isotope becomes plutonium-240, which then undergoes spontaneous fission. This means that plutonium-240 in a bomb can lead to fission before the bomb can even be assembled, leading to fizzle. Let's look up some more for this fizzle. You have fission here, you have fusion, and you have fizzle. The reaction of plutonium in a nuclear bomb. We have fission, the isotopes U-35 and Pu-238 were selected by the atomic scientists because they readily undergo fission, and this fission occurs when a neutron collides or strikes the nucleus of either the U-235 or the Pu-239 nucleus. And when this happens, more neutrons are formed. It split the nucleus into fragments, releasing tremendous amount of energy. Now each fission yields a little over 200 mega electron volts, or about 82 TJ per K. Now the main isotope of plutonium, Pu-238, which has a half-life of 88 years, and alpha decay to U-234, releasing 5.6 mega electron volts, and Pu-239 fizzle, half-life 84,000 years, and alpha decay to U-235. You're looking at plutonium with atomic number of 94 and an atomic, this is saying 231. This is probably one of the most stable, but I've seen plutonium to be yes, that is 231 on the periodic table here, or the partial periodic table, but I've seen it where it was 244, so that must have been an isotope. All right. So plutonium is a silvery gray metal which becomes yellowish when exposed to air. And most plutonium in a microscopic most plutonium in the air are microscopic particles resulting from nuclear weapons testing and nuclear reactor accidents. So that's where you go with most of the plutonium that is in the environment, in the air. It's mostly from microscopic, it's a microscopic plutonium which results from nuclear weapons testing and nuclear reactors accidents. Now in fission reaction, an atom with large atomic number, such as thorium-232 and uranium-235 and plutonium-239, are split into 2 or 3 other atomic number and elements when a neutron is absorbed. So Pu-232, U-235, and Pu-239, thorium-232 rather, uranium-235, and plutonium-239 are split into 2 or 3 whatever the atomic number and elements when a neutron is absorbed. So when they absorb a neutron, these thorium-232 and uranium-235 and plutonium-329 undergo fission, and they, split the nucleus and produce some more neutrons there, 3 more neutrons, and usually some other different isotopic elements. This fission releases large amount of quantity of energy. Now, one problem with plutonium in nuclear reactors, this is a problem. Now, the real problem is using plutonium in a nuclear reactor is the delayed neutron fraction of plutonium. The delayed neutron fraction of plutonium. Now, most neutrons in a nuclear reactor are called prompt neutrons. Yeah, most neutrons are called prompt neutrons. And they are emitted within 10 exponential minus 14 seconds. So within the time limit of 10 to the exponential minus 14, that is about each to the minus 14 seconds, they are emitted. So that's why they're called prompt neutrons. But the problem with plutonium is that you have a delayed fraction. And this delayed fraction poses a problem because what we want is the prompt neutron. Now, plutonium-239 is more frequently used in nuclear weapons than uranium-235 because of the Pu-235 is easier to obtain in a quantity of critical mass. Now both Pu-239 and uranium-235 are obtained from natural uranium, which primarily consists of or containing uranium-238, which has a 99.99% abundance in nature, and it's more stable, and contain traces of other isotopes of uranium U-235. All right, we'll take another little break here while we come to finish up with plutonium. And as we go, plutonium, atomic number 94, atomic mass of 231, its electronic configuration as radon 86 224. I don't know if it's 222 or 226 there, but radon, and I believe 7s2. But let's get it in order here. Rn 5f 5f6 7s2. I have to certify this because it doesn't have a 6D into this electronics configuration, and I believe it should have had. So I'm going to have to certify this electronic, but certainly it's going to be radon 5x6, probably a 6D 14 or something like that. I don't remember. And 7s2. So we'll have to certify this electronic configuration of plutonium. And we'll do this when we return with plutonium.